Welcome to the second part of Chapter 5. In this part we are going to discuss folds and folding. Folds are very common and very attractive structures. They appear in a large variety of shapes and scales, and most folds form in response to some form of lateral shortening of layers. Let's recap some basics on fold geometry, on the elements of folds. We see here two examples of synformal and antiformal folds. The center of strongest curvature would be the hinge zone with some hinge points that we see highlighted here. If you connect the hinge points with a line and you draw a second line along the hinge line that we see here, we obtain the actual surface. On either side of the hinge zone we would find the two limbs, which in this example here connect antiformal hinges with synformal hinges. The angle between the limbs is the interlimb angle. The wavelength is measured from synform to synform or from antiform to antiform. The amplitude is the height between a hinge and the inflection line, which we find typically about halfway along a limb between the two neighboring hinges. We also see here that folds along the hinges often are non-cylindrical. That means that the hinge is curving, and this might result in different plunge directions of the hinge line that you can measure in the field. Cylindrical folds have straight hinges, but this straightness of a hinge is also scale dependent. You might find cylindrical folds over a few hundred meters, a couple of kilometers if you are lucky, but large scale folds almost always show variable hinge orientations. Fold attitudes can be described in a number of different ways. Here we see a very simple kind of bend in some layers. This would be referred to as monoclines. We see here synformal and antiformal folds. This refers simply to the direction in which the fold is convex. Synformal folds are convex downwards, antiformal folds are convex upwards, and this is irrespective of the stratigraphic succession of the layers. This would, for instance, apply to folded metamorphic rocks where there is no age difference between the layers. If these are metamorphic layers, we can expect that a layer that is tectonically higher up in the sequence is of the same age as a layer that is further down. So in metamorphic terrains you typically would refer to folds in terms of synformal or antiformal, unless you have good reason to believe that certain layers are younger than others. In lower grade rocks, where you still preserve primary sedimentary layering and the stratigraphic succession is known, you would use the terms syncline and anticline. Synclines are always convex towards the older layers, as we see here. We have here this symbol that indicates the younging direction. Here clearly the younger layer is on the concave side of the older layer, and the older layer is on the convex side of the younger layer. In an anticline that would be just the other way around. We see here the convex side points towards the younger layers, the younging direction is upwards here in this orientation. In many cases, synclinal folds are also synformal folds because here they are convex towards the older layer, and also the convex directions is downward. Here it's an antiformal anticline, the convex side points upwards, and the layers are also convex towards the younger layers. But that is not necessarily always so. Here we see, for instance, a synformal anticline. The shape is synformal because it is convex downwards, but we see here that the stratigraphic succession is overturned. We see here a younger layer is underlying an older layer. And in the antiformal syncline, this is just the other way around. It is an antiform because the fold is convex upwards, but it is also convex towards the older layers. We see here an older layer is overlying a younger layer in an antiformal fold shape. How do we get to synformal anticlines and antiformal synclines? That is almost always related to polyphase folding, and we see how that works here in the diagram at the bottom. The first fold to form would have been this fold here. This is a tight, perhaps isoclinal fold where we formed an upper limb and a lower limb, which initially were limbs of planar shape. In a second folding event, these two limbs were undergoing a second episode of folding, and that produced the folds that we see here, where folds in the upper limb are mimicked by folds in the lower limb. This means that the folds in the upper layer here form the normal stratigraphy. The younging direction is still upwards, and we find here an anticline that also happens to be antiformal. We find a syncline that is synclinal, and we find another anticline which also follows an antiformal shape. This is different in the lower limb. In the lower limb, the stratigraphic sequence is overturned due to the first folding, and here we see a younging direction downwards. That means that, for instance, this synformal fold is actually an anticline because it is convex towards the younger layers, but its shape is synformal because it is convex downwards. So, antiformal synclines, synformal anticlines can occur in terrains that have undergone polyphase folding where the stratigraphic sequence is turned upside down. Classification schemes have been discussed in an earlier series of videos made for first year level. I just want to remind you there is the very useful floaty diagram which makes use of the dip of the axial surface and the plunge of the hinge line, which allows you to categorize your fold in terms of, for instance, steeply inclined, moderately plunging folds. And in addition to that, we can use the interlimb angle, which again is categorized into isoclinal folds where the limbs are parallel to each other, tight folds where the interlimb angle ranges between 0 and 30 degrees, or close or open or gentle folds, which all have their interval in interlimb angles. Let's come to the mechanisms that allow different fold shapes to form. There are two important ones, the flexural slip folding and the shear or similar folding. Let's start with the flexural slip folding, which also is called concentric folding. Here we see an example of such a fold, and the characteristics of the fold is that several layers are bent around one center. We see here the center of the fold, and we see that all the layers outside are bent around the same center. Obviously, that is where the term concentric folds has its origin. We also see that the thickness of layers, if we follow the layer from one limb through the hinge to the other limb, remains constant. That is the most striking and easily recognizable characteristic of flexural slip or concentric folds. We also see that different layers have different fold width, depending on where they are positioned within the fold structure, whether they are close to the core or further outside. The outer arcs are wider than the inner arcs. Another geometric requirement for flexural slip or concentric folds is the cuspate geometry in the center of the fold, where we frequently find some more ductile material, softer material. Typically these would be siltstone or shale material underneath folded quartzites, and we find a tectonic boundary at the bottom where the folded strata end and are underlain along a tectonic contact by unfolded strata. If we remember the folds that we have seen in an earlier video in the context of flat ramp structures, these folds that we see here are essentially concentric folds. We can see here, for instance, the constant layer thickness from one limb through the hinge onto the other limb. Also up here we see that quite nicely, that the layer thickness remains constant along the folded layer. This type of folding creates mechanical problems. Concentric folding requires that we are stretching the outer arcs more strongly than the inner arcs. The inner arcs, in fact, are undergoing contraction in the hinge area, whereas the outer arc is undergoing extension. At relatively low temperature, this will result in a number of structures that sometimes can be recognized in the field. If the outer arc is undergoing stretching, we will find that tensile fractures are forming perpendicular to the layers, and these tensile fractures might open up with increasing folding and with increasing tightening of the fold. The contraction in the inner arc is often compensated by conjugated faults. In this orientation, these would be conjugated thrust faults. In between the outer arc, that is undergoing extension, and the inner arc, that is undergoing contraction, we find a neutral surface where neither stretching nor contraction occurs. However, in nature, we do not often observe these contractional features in the inner arc and the extensional features in the outer arc. Instead, more commonly, we see flexural slip folding. And flexural slip folding means that the extensional strain in the outer arc and the contractional strain in the inner arc is compensated by sliding of layers along the layer boundaries. This compensates for the extension of layers in the outer arc and the shortening in the inner arc during concentric folding if no such movement along the layer boundaries is possible. So let's have a closer look at flexural slip folding. We will see that the flexural slip along layer boundaries will create opposite sense of shear on opposite limbs. We see here on the limbs next to an antiformal hinge that the hanging wall transport points towards that antiformal hinge zone on either limb. In synformal hinges, we see that the hanging wall transport during flexural slip folding is away from this limb. But in either case, the shear sense on the limbs next to a hinge is opposite to one another. What that means is factually that during the bending of that layer, we also find brittle displacement along the layer boundaries. Here we see a more prominent illustration of the features that are associated with flexural slip folding. Again, we see here an antiformal hinge. We see the hanging wall transport on either side towards that hinge, and we see striations forming on the layer surface in consequence to the flexural slip along the layer boundaries. We also see that the hinge line that is oriented in this direction is perpendicular to these stretching, to these striations, to these transport lineations that we would find. These transport lineations are practically identical to fault striations, only that they are here related to flexural slip sliding along layer boundaries. The opposite sense of shear along the opposite limbs can be seen by identifying slick inside steps. The second important type of folds are similar folds or shear folds. In contrast to concentric folds or flexural slip folds, which are typical for the brittle ductile transition and relatively cold temperatures, similar folds form at high temperature because they require effective ductile flow in order to form the shapes that are characteristic for them. The main characteristic feature for similar folds is that the layers are thicker in the hinges compared to the limbs. We see that here quite prominently in the lighter colored layers, which are almost twice as thick in the hinge compared to their thickness along the limbs. That means that during folding, material is transported by ductile flow from the limbs into the hinges, and that requires a very efficient ductile flow, which we find only in the higher temperature middle and lower crust, not so much in the ductile part of the upper crust. If we compare the geometry of concentric and similar folds, we see the reason for the naming. Similar folds do not change their shape throughout a folded sequence. We see here that the interlimb angle and the fold shape is identical. We find layers of different thickness, but if two layers have the same thickness, like this layer here that has a hinge thickness of 10 units, whatever they may be, we see that this layer and that layer are identical. You could cut out this layer, move it upwards, it would match perfectly the layer up here. That is not the case in concentric folds. The inner layers in concentric folds have a different shape compared to the layers in the outer part of such concentric folds. Here we see an example of similar folds. We can follow here layers of different thickness. We beautifully see how the layers are thinning out along the limbs and are intensely thickened in the hinges. This particularly applies to these lighter colored layers. The thinner layers that we see here are more competent and ductile flow is not as effective, and therefore the changes in thickness between the limbs and the hinge is not as prominent. But the light gray layers here show very clearly a strong thickening in the hinge compared to much thinner limbs. Another important feature that we observe in folded terrains are folds of different order and parasitic folds. Let's find out what we mean by that. If we follow the orange line here, we see that overall this layer is folded into one major antiformal and one major synformal fold. That is what we would call the first order fold, the largest fold structure that the layer follows. But when we look carefully, we see that the layer in fact follows a more intricate system of smaller scale folds that are developed on the larger scale limbs and in the hinges of our first order fold structures. These are the second order and the third order folds. That means very often we find folds of different scale, and in the field you might observe folds of meter scale or 10 meter scale in an outcrop that belong to much larger folds in the larger scale. Here we see an example of two orders of folds. We see a similar fold that follows here an antiformal shape, but some of these layers also form smaller scale folds. In particular, the thin black layers show that here are some asymmetric folds on the one limb. We also see some of such asymmetric folds on the opposite limb, and in the hinge of the first order fold we see some smaller scale symmetric folds. So the first order fold, indicated in orange, is supplemented by the second order fold in the thin dark layers. These second order folds also are called parasitic folds. We often can see different orders of folds also on geological maps, and here we see an example of a map from South Africa, from the Grahamstown area, where we have a sequence of the Weltevrede Formation, which is an older layer compared to the Whitport Formation here in light blue color. There's also a even younger green layer here, which is the Lake Mens subgroup, again overlying the Whitport Formation. From the distribution of rocks and the lobate shape of the formation boundaries, we can see here that in the center of a large fold, the oldest layer, the Weltevrede Formation, comes to the erosion level, and it is surrounded on either fold limb by the younger Whitport Formation. That indicates a large-scale anticlinal structure in approximately this position. Let's look a little bit closer at this area here, at the fold closure of our first order large-scale anticline, and we see that here in our close-up. The first order anticline would cut through somewhere here, but we find there are further lobate and cuspate shapes which indicate that there are further smaller scale structural elements, and one of them is already indicated here in the form of the symbol for a synformal fold. The same applies to a position approximately here. Also here in this region we find a younger layer surrounded on either limb by older strata, and these are second order synclinal folds that are parasitic to the larger scale anticline. Let's find out how parasitic folds may form, how they develop over time. Let's assume a sequence of layers of different competence that are undergoing horizontal shortening in an environment where ductile deformation is possible. In the first stage, a initially planar layer, like this black layer, would undergo symmetric folding in response to the lateral contraction. In a further stage, this folding would affect the entire sequence, and we would find that originally horizontal layers become tilted, and they become tilted in opposite directions. We see here a larger scale limb is here dipping to the left hand side, the opposite limb is dipping to the right hand side. At the same time, we assume that the shortening direction remains the same as in the first stage of the process. And this will expose these two limbs dipping in opposite direction to shear stresses that are opposite to each other. On the left-hand limb, we would see that the shortening direction creates a shear strain that is opposite to the shear strain on the opposite limb. In this case here, top to the right, on the opposite limb, top to the left. This shear strain will have a dragging effect on the folds, which initially were symmetric. And the asymmetry of these folds is opposite on either limb. We see here a long, short limb geometry that is just mirrored and opposite on the other limb. Here again, long and short limb geometries, just mirrored compared to the limb on the left-hand side. In the hinge of the fold, we see that the layer is still parallel to the shortening direction. And here we maintain the symmetric geometry of the folds. We might tighten them compared to the earlier stage, but the fold shapes that we find in the hinge is still symmetrical. We can associate these different shapes of folds with letters. We see here a long, short, long geometry which looks like a Z shape, just tilted to the side. We find in the hinge the symmetric shape that mimics an M or a W, and on the opposite limb we find a long, short, long limb geometry that reminds us of an S shape. We can see that here a first order fold has developed at a larger scale, but at the same time we see the development of these asymmetric folds on the fold limbs and the symmetric folds in the hinge, which are parasitic folds, which are second order folds compared to the larger scale first order fold. Let's have a look at an example. Again, here our parasitic folds in our shear fold that we have seen earlier. The first order fold and the second order folds developed during the same time. They belong to each other and they represent the same folding episode. Here we see a cartoon that shows parasitic second order and the corresponding first order fold in 3 dimensions. We see a Z-shaped parasitic folds on the one limb, the S-shaped parasitic folds on the other limb, and MW folds in the hinge zone. We also see that the hinge lines and the actual surfaces of the smaller scale parasitic folds are roughly parallel to the actual surface and the hinge line of the larger scale first order fold. We are going to see in a moment how we can use this as a tool during field mapping. Let's assume what we see here is an outcrop of a layered folded sequence in a road cutting or in a rock face in a quarry. We see here that there are layers that have small scale folds with long, short limb geometries, and these long, short limb geometries, they are changing when we map across such an outcrop phase. We will see that in some layers we find small scale folds that follow a Z-shape geometry. That would apply to this layer and to that layer, and also to this and that layer, but not to this and to that layer, which show S-shape geometry of their long and short limb parasitic folds. Here we see the result of the analysis. We see that these Z shapes are pointing upwards to an antiformal fold closure. The shape indicates that this must be here the normal layer, and the layers that show the S-shaped geometry of our parasitic folds are part of the overturned limbs. This identifies the antiformal fold closure. It also identifies the synformal fold closure, which brings us back to the limb with the Z-shaped parasitic folds. We can introduce our three-dimensional view of fold structures in comparison to the two-dimensional sections that we see here. Again, we see here Z-shaped folds on the upper normal limb of an antiformal fold and the S-shaped folds on the overturned limb. This is exactly as we see it here in this area. We see that this limb could not be connected to this limb via a synformal fold closure. It must be an antiformal fold closure, because otherwise the Z and S shape parasitic folds would be on the wrong limb. For the synclinal structure that we see here, we see again the corresponding 3D sketch with the S-shaped folds here on the upper limb, following through the hinge onto the overturned limb, which then has here the Z-shape asymmetry of folds. Thank you very much for your attention.